Hi guys, welcome to another Learning Electronics Repair video. Today I want to chat to you about the humble ESR meter. This, without doubt, is one of the most useful tools you can have in your toolbox, and yet I know many of you guys don't have one. So I want to show you today how the ESR meter works, what it was designed to do, and then some probably quite surprising things you can do with it that you may never have thought about. And these probably aren't all of the things you can do with this. I'm still finding useful things to do with my ESR meter. So let's first have a look to see what ESR actually is and how the ESR meter measures it. ESR stands for equivalent, series, resistance. I'll write it out so you have plenty of time for that. So again, equivalent series resistance. What is it? Well, it's a property that capacitors have, and in particular we use to test electrolytic capacitors. So a capacitor, if we connect it between a supply plus and minus, and we'll make it an electrolytic capacitor. Once the capacitor charges up, so when you first apply power, the capacitor will charge. Once that has occurred, the capacitor blocks DC. So effectively the capacitor is open circuit. After it's charged up, practically no current flows through it. So that's how a capacitor behaves with DC voltage, and we will see, we'll check this in a minute with our multimeter, that it's effectively an open circuit. However, capacitors behave differently to AC signals. So to an AC signal, the capacitance basically, or capacitor, basically forms a circuit. So when we apply AC to a capacitor, current is flowing backwards and forwards, alternating current going backwards and forwards, and the capacitor will pass AC. The amount of current it will pass depends on the frequency of the AC. The higher the frequency, generally speaking, the higher the current, and also the value of the capacitor. Generally speaking, the higher the capacitors, the higher the current. So that's what a capacitor does. It passes AC, it blocks DC. So DC blocked, AC, yes. But when a capacitor is passing AC, it's not exactly a short circuit to AC. As I mentioned, the amount of current it will pass depends in particular on the frequency of the AC and the value of the capacitor. So basically a capacitor passing an AC current is the equivalent of a resistor. So imagine a resistor in parallel with our capacitor, and the resistance of this will affect the amount of current that flows. And this is what we're talking about when we say equivalent series resistance. So a capacitor, an ideal perfect capacitor, would be open circuit to DC and short circuit to AC, basically. But there's no such thing as a perfect capacitor. However, some capacitors are better at passing an AC signal than others. And this becomes important in high frequency circuits, especially high frequency switching circuits. So switch mode power supplies, buck converters, DC to DC converters, these sorts of circuits need to have capacitors that are low ESR. And it's important. If the ESR of the capacitor is too high, the power supply won't work properly. If it's badly out of spec, it's much higher than it should be, much higher than it was designed to work with, you could blow the MOSFETs that are driving it, or the transistors, so you can actually blow the power supply up because of bad capacitors. This is why it's important to test capacitors for ESR. Not only in switching circuits, in audio amplifier equipment and other applications, it's also an important factor. So let's have a look how we actually measure ESR. So here I have some capacitors. This one's 1000 microfarad 16 volt. This is 820 microfarad 6.3 volts. These are both low ESR capacitors. I have another one, 1000 microfarad 6.3 volts, another low ESR capacitor. Let's see if we can measure this equivalent series resistance using our multimeter. So we've got the multimeter on ohms range. We'll use a polarity, so negative of the capacitor to the black lead, yeah, positive to the red lead. What happens? Well, we get a reading initially, and then we're reading a very high resistance, 1.8 mega ohms on that one. Okay, try another one. Again, we'll attach our meter probes. We see resistance climbing up, 403 kilo ohms, 404 kilo ohms, 405, still climbing slowly, yeah. So we do see a resistance. Let's try one more. Again, we'll connect the leads. I'll try not to touch them. 1.78 meg, yeah. So basically we are reading a resistance when we measure the capacitance on the multimeter. We're now reading a negative one, yeah? The reason we're reading a negative one is because the capacitor has some charge in it, it's charged in the other direction. If I short the capacitor out, yeah, and we read it again, now we don't need a negative, yeah? And again, it's climbing up. I'm just going to get a good connection onto it. 3.3.5 mega ohms, yeah? So, is that resistance the ESR? Well, actually, the answer to that is no, that is not the ESR. What we're seeing is the initial reading, for an instance, is the capacitor charging up, and then after that, we're actually seeing the leakage current. So, electrolytics in particular will have a little bit of leakage, so even with a DC voltage across them, they're not exactly an open circuit. As you can see, they're reading to the mega ohms. One's reading quite a bit lower, which may actually be a faulty capacitor, but that is not the ESR. To measure ESR, we need to apply an AC signal, and this is why we need an ESR meter. So this is my ESR meter, MESR-100. There are other models available. We'll talk about that a little bit later. This was about €40, something like that, and I've had it for about 8 years now. And this has paid for itself over and over and over again. So we'll switch it on. This one actually has a few ranges. So if we go to mode range, it has a 1 ohm range, it has a 10 ohm range, it has a 100 ohm range, yeah? To zero it, we need to connect the two leads together. So let's just zero our meter. Yeah, set pretty much to zero, hit the button. It's zeroed, close enough. Okay. Let's now have a look at some of our capacitors. So we'll connect them again, observing the polarity, black to negative. What do we see? Well, this is reading 0, 0.3. Let me just change the range. I'll put it onto auto range. That's an auto range. Okay. So that's reading 0.02 of an ohm, roughly, a little bit lower, yeah? That is a low ESR capacitor, yeah? Let's have a look. That one's the 1000 microfarad 16 volt. Let's look at the 1000 microfarad 6.3 volts. That's a little bit higher, 0.05. It's actually more common for a lower voltage capacitor to have a lower ESR. That's because the dielectric inside the insulating layer is thinner, basically. But as you can see, the ESR will vary from brand to brand. This one's a Sanyo, this one's Chong X, and this appears to be actually the lower ESR capacitor. This is another one, KZG. Let's have a look. That's reading very low. Yes, that's another low ESR. Now it's telling us here that for capacitors 25 volt, yeah, the capacitors with low ESR. So it's saying if it's a 25 volt capacitor or lower, it's a low ESR. Okay. So that's what the ESR meter does. Now, how does it do it? Well, as I explained earlier, it does it by passing an AC signal through the capacitor, and we can actually see that on an oscilloscope. Here's one of my oscilloscopes. This is actually my Tektronix analog. I have two others. I have the digital Rigol above it, you can see, and I have another analog scope as well. But this is the one that was closest to hand, so we can use this. So if I connect the ground lid of my scope to the ESR meter, yeah, and I connect the scope probe, what can you see? Well, you can see a waveform on there, yeah. It's not quite a sine wave because it's almost certainly digitally generated, but it's a close approximation of a sine wave, and that is what the ESR meter is generating. It's roughly about 1 division per cycle. It's very close to 1 division. It's on 10 microseconds per division, so that's actually 100 kilohertz, which I know anyway because it says on here 100 kilohertz in circuit testing. So that's how an ESR meter actually works, by generating a high frequency AC signal. Let's have a look now at some bad capacitors. These are low ESR capacitors taken from a motherboard. I'm sure you can see by looking at them, they are visibly bad. The electrolyte has been leaking out of them. That is not a good thing with a capacitor. So let's have a look to see how these read. Just click the ESR meter on. Okay, so we have 0.65 of an ohm. Now that might not seem bad, but it is. In fact, the meter is telling us that that is good if the capacitor is less than 200 microfarads. It's not. It's actually a 1800, I believe, this one. 1800. I'm not quite sure if you can see it very clearly. 6.3 volts. So that is a bad capacitor. So I've got another one. This looks even worse. Yeah, 0.894 of an ohm. The worst I've ever measured was actually more than 100 ohms. It read open circuit. So we can get some bad ones. I've seen quite a few that are 10 ohms and more. So that's how you can find bad capacitor with an ESR meter. Let's have a look at these on the capacitance meter as well. So here's my capacitance meter on the 2000 microfarad range. Let's look at our bad capacitor. Let's see what it's reading. Sometimes they'll read bad, like half the value they should be, but sometimes they read actually okay in capacitance. Okay, this one's reading about 700 microfarads, so it's obviously bad on there as well. Let's have a look at the other one. But it is possible, and I've seen, and I've even shown on this channel sometimes, again that's a bad one, sometimes capacitors that read bad in ESR, but they read okay in capacitance. Here's some more. So this one is obviously gone. This is a 3300, 6.3. Since I have the capacitance meter, let's check this one. I have to go up a range. This is actually reading 5,000, 6,000, yeah, roughly double its value. Let's look at this one. So this is another one that isn't leaking, but it is bulged. Can you see the top of that is like curved outwards? It's like a dome. It's convex. Yeah. What's this one reading? Again, this reads much higher than it should be. Now, this is another way that sometimes capacitors fail. These will probably read okay on the ESR meter, but they're obviously not. I mean, this one clearly isn't. Yeah. But we can have a look at the capacitor. See, now that reads good ESR, but the capacitance is about double what it should be, and it's visibly a bad capacitor. That's something to look out for. Some capacitors, certain brands or types, will fail in this way. Yeah, they'll fail in this way. So you really should measure both ESR and capacitance. This one is the one that's bulged on the top a little bit. We know from that it is faulty, and the fact it's reading about twice the capacitance it should do. But again, the ESR reads low, so just bear that one in mind. I'll just get one or two non-low ESR capacitors. These are not low ESR. Let's just use them for comparison. This one doesn't say it's low ESR, but let's try it. And you can see that's reading much lower. Yeah. So even with good capacitors, you can use your ESR meter to select them when you're building projects, such like especially if you're using salvage components. That's another very good reason to have an ESR meter. But this can do quite a bit more than just test capacitors. So let's have a look what else we can do with it. Yeah. There's another type of component which reacts differently to AC and DC, and that's an inductor. So can we use the ESR meter to measure inductors? The answer is yes, we can. So I'm going to show you now how to use the ESR meter to test an inductor to see if it's the correct value, and B, how to measure the value of an inductor where the value isn't marked on it. With an inductor, if we apply a DC voltage to the inductor, plus to minus, the inductor passes DC. It's practically a short circuit as far as DC is concerned, especially a small inductor. A very large one would read a bit of resistance, but it's basically a short circuit. And if you put your multimeter across it, that's what you will read. Yeah. So when you apply the voltage to an inductor, actually for a fraction of a microsecond or however long it takes, the current will charge up the magnetic field in the inductor, and once it's fully magnetized, the current will pass straight through it and it will act like a short. And we can test that. We can use our multimeter in the meter and see how an inductor reads. With AC, it's different. So if we apply an AC signal, what happens is the current's going backwards and forwards, and each time it reverses direction, it has to magnetize the coil first in one direction, and then when the current reverses, it has to collapse that field and magnetize in the other direction, and so on. So the fact that some of the power is being used to magnetize and demagnetize the coil very rapidly means effectively it has a resistance to current. It acts like a resistor and looks like a resistor, but the value of the resistor will depend on the frequency. So at a higher frequency, it looks like a higher resistance. Yeah, at a lower frequency, it looks like a lower resistance, and the resistance is actually called reactance. Yeah, reactance. But as far as we're concerned, for test purposes, we can consider it to basically be a resistance. So when you apply an AC signal, the inductor to the AC looks like this. Yeah. It looks like a coil, an inductor, with a resistance in series. And as I say, the resistance will vary, or appear to vary, depending on the frequency. The higher the frequency, the higher the resistance. So that's how it looks, the equivalent circuit. Opposite to the capacitor, where the resistance appears in parallel with it, with inductor it appears in series with it. Okay. Now we know our ESR meter applies an AC signal, and it's marked on it. I showed on the oscilloscope. It's 100 kilohertz. So we know the frequency. Yeah, there's a formula, the reactance formula, that we can work out what the equivalent resistance is for a given frequency. And this is where we do a bit of maths, but don't let this worry you for more than a minute, because I'm going to make it very simple. Okay. So the reactance, or to what we consider the resistance in ohms, yeah, is 2 pi FL. That's the formula, yeah. 2 is the number 2. Yeah, it's a number 2. Regardless how much you hate maths, 2 is still 2, yeah. 1 and 1 is 2. Pi is, I'm sure you know, a mathematical constant, and roughly speaking, it's 3.14. That's good enough for our purposes. So this formula becomes a bit simpler now. It's actually 2 times 3.14 times the frequency. Now the frequency is in hertz for the formula. It's in hertz. Ours is 100 kilohertz, so F is 100,000. And they'll never change as long as we use the same type of ESR meter, or we know the frequency of our ESR meter. That effectively becomes a constant. It doesn't change. Only the inductance changes that we're measuring. Yeah. The inductance for the formula is in henries. Yeah. Now, a henry is a very large inductor, and in our cases, they'll be much smaller than that. Yeah, they'll be much smaller than that. So I'll show you how the formula works in henries, and I'll show you how to do it in micro henries. It's much easier. Okay. Let's work out what the resistance would be if we had 100 micro henry inductance. Yeah. So 2 times 3.4 is 6.28 times 100,000 is 628,000. Yeah, and that's a constant. That's never going to change. 628. It's always going to be 628,000. So we don't have to worry about 2 pi f. 628,000. Yeah, and the resistance is going to be 628,000 times the inductance in henries. This is where it starts getting a bit messy. So 100 microhenries is 0.00. Well, the next would be 1 millihenry, which 1,000 microhenries. That was 100, so it's 0.00100 if you like. That's why it gets messy, yeah. But if we work this formula out on my calculator, we'll work out what the resistance is, and I'll show you how to do it easier. So here's the calculator. So we have 628,000. We have it off the screen. Let's go again. Yeah, we have 628,000. Yeah, times 0.001. 0.0001. Sorry, yeah. I almost messed it up. See how fiddly it is. Yeah, equals 62.8 ohms. So the resistance we read on our ESR meter at 100 kilohertz should be 62.8 for 100 microhenry inductor. Yeah. Now let's make it simpler. If we just want the value in microhenries, 100 microhenries, we can get rid of that, and that becomes 100. Yeah. And now we've got to move some decimal points from here. 1, 2, 3, 4, 5, 6 decimal points. Yeah. So from here we go 1, 2, 3, 4, 5, 6. The decimal point is now there. So the formula, if you just want the answer in microhenries, and that's perfectly fine for just about anything we want. Yeah. The formula is R equals 0.628, and that'll never change. It's always 100 kilohertz, yeah, and I'm pretty sure all ESR meters probably are. So it's 0.628, yeah, times the value of microhenries, 100. And I'm sure you can see without using the calculator, 100 times 0.628 is 62.8. It's the same answer in ohms. Yeah. So there is your formula for working out the resistance of an inductor. R equals 0.628, messed it, or, let's do it again, R equals 0.628, because this is important, times the inductor in microhenries. That is it. That is your formula. If you remember that, stick a label on the back of here, 0.628 times inductance in microhenries. Yeah? So that's how we can work out what the resistance of an inductor should be. And we can measure it and test it and see whether it's reading correctly. Yeah? But more likely, we're going to want to know the value of an inductor that isn't marked. Yeah? We could do all the same maths, but I'm just going to give you the formula. I'm just going to give you the formula. I'm not going to make you go through all this again, yeah. So if we want to know the value of the inductor in microhenries, the formula is, yeah, ready for it? Resistance that you read in ohms, yeah, that's the resistance you read on your ESR meter in ohms, divided by, ready for it, 0.628. Okay? So that's it. We measure the resistance on the ESR meter, we divide it by 0.628, and that's how many microhenries it is. Yeah? There you go. Let's put this to the test. Yeah? Let's put it to the test. So here's the ESR meter. Now this is a 100 microhenry inductor. I bought them from AliExpress and it says 100 microhenries. It isn't marked on it, but I bought them as 100 microhenries. So let's see what we've got. Okay? We have 61.3. Yeah. Now we've already worked out 100 microhenry inductor should be 62.8, and we're actually reading 61.2 ohms. Yeah. So our inductor is reading a little bit less than expected, but they're not going to be that accurate, are they? So it's about right, yeah? It's about right. So what value is this according to our meter, if our meter is correct, yeah? Well, that's this one, yeah? R is, we've measured it, 61.2 ohms, divide it by 0.628. Let's see what we get. Use the calculator again, yeah? So R, we measured it. Let's clear all the settings. 61.2. And we can divide it by 0.628. 0.628. Yeah? 97.45 microhenries. Close enough, isn't it? Yeah. Should I tell you how to remember this one here? There's a mnemonic here. 6 plus 2 is 8. If you can remember 6 plus 2 is 8, you always know it was 0.628. Yeah. Let's try a few others. So this one is marked on it. I'll zoom down so you can see it actually. So you can see it's marked R60. It's probably not coming out very well against the white paper. Let's do that with it. Yeah, R60. So we know, if you know anything of the codes, that is 0.6 of a microhenry. Yeah, that's 0.6 of a microhenry. Let's measure the resistance across them and work out what it is. So we should know what this one is. 0.6 of a microhenry. There's no polarity on an inductor, just connect the leads. And let's see what we've got. And we've got 0.355, yeah? 0.355. Now we have a formula, don't we? So 0.355 divided by 0.628. Let's see what it is. Let's see what it is, yeah. 0.355 divided by 0.628. Well, it's 0.56 microhenries, yeah, 0.565. And that says 0.6. So that's good enough, don't you think? That's good enough. Let's do one more. So this one is an inductor. You can see it's an inductor, it's a coil. There's no sensible value marked on it. I don't know what it is. So let's see if we can measure it. Okay. So what have we got? 27.7. Yeah, it's less than 100 microhenries. You can figure that out. 27.7. So again, let's do the formula and work it out. Okay, calculator again. So 27.7, that's what we measured in ohms, divided by 0.628, 44 microhenries. It's probably a 45. So there you go, guys. That's how you test inductors and how you measure inductors with an ESR meter. 0.628. Just remember it, 0.628. Yeah. The resistance equals 0.628 times the inductance, and the inductance is resistance divided by 0.628. Stick the formulas on the back of your meter. Just stick them on there with a sticker. Yeah. That's all you need to do. Here's another thing we can do with our ESR meter, and that's to find short circuit high side MOSFETs in VRMs, on graphics cards, on motherboards. So we have an old motherboard, we have a VRM powering the CPU, and you can see we have 1, 2, 3, 4, 5, 6 coils. Okay, so there's 6 phases in the power supply, and each one has a group of 3 MOSFETs. Yeah. And what I've done is I've simulated a fault by putting a short circuit on this one, on this phase. Now, if we look with our ohm meter at our VRM, and we compare first of all from 12 volts in to ground, so here's your 12 volts in, you'll see we're reading about 7 ohms, yeah? And that is the resistance of the CPU. So if we were to switch this on, the 12 volts would go directly into the CPU. Hopefully the ATX power supply would trip out, but possibly not before damaging some things, yeah? If we go to the short circuit I've put on here, you can see it, yeah? But if we go to the other MOSFETs, the short is everywhere, and we can't see a difference between the reading on any of them, yeah? They all read the same. So how can we find the short? Well, one very good way to do it is to use the ESR meter. And the way we do this, I'll show you first and I'll explain how this works, yeah? So these are the inductor coils. I'll zoom down a little bit so you can see it a bit clearer. Okay, you can now see 1, 2, 3 inductor coils, and the other ones are up over here just off shot, yeah. Let's see if we can find the short circuit one. So what I'm going to do is measure with the ESR meter across the inductor. Yeah. Let's see what we get. So this is actually the bad one. 0.022, yeah. This is one of the good ones. 0.43, yeah. Another one. 315. Try this one again, see if I have a good connection on it. 315 had a bad connection. This one, 0.025. So we can see straight away the one which has the short circuit MOSFET, this phase, is the one that reads much lower than the others. Now let me explain to you how that works. To understand how this works, you have to understand a little bit about VRMs. Now, I've covered this before, but I guess there's some guys here who are new to this, so let's just do it once more. VRM, we have 12 volts coming in. We have 2 MOSFETs going to ground. Yeah. And the MOSFETs come from a controller that basically switches them on and off rapidly. Yeah, there's resistors in here and there's other stuff in here, but there you go, yeah. So these switch on and off in turn very rapidly. From here we have the inductor, and then this goes to the CPU, yeah. Now I'm putting my ESR meter across here and across here, yeah. And on the bad one, I'm reading like 0.002. And on the good ones, I'm reading about 0.370. Why? Well, I'll tell you why. We know that inductors appear as a resistance to the ESR meter, yeah? We've just looked at that. We know that capacitors appear like shorts or very low resistances, low ESR, to the inductance meter. Okay, your CPU on here will have lots and lots of capacitors going to ground. Yeah, lots of them. Many, many, many. Electrolytics and other little capacitors going to ground, yeah? Okay. The 12 volts will have, wait for it, lots of capacitors going to ground. Yeah? In a good circuit, these MOSFETs, to your ESR, you've seen it's a very low voltage, 100 kilohertz signal. It's not enough to make the MOSFETs conducting anyway. They switched off, there's nothing driving them. So as far as your ESR meter is concerned, basically, on a good phase, that's an open circuit. There's nothing can flow that way, yeah? So what you measure on your ESR meter is the resistance of the inductor. Yeah, that's that one. And as we've just seen from that in ohms, we can go and work out the value of the inductor, but we know it's about 0.6 microhenries because it's very similar to the one we just looked at. Yeah, something like that, 0.6, 0.7 microhenries. So on all the good phases, what you see is that, the resistance of the coil. On the shorted phase, this MOSFET here is short. Yeah. So you've now got a direct connection here, a short circuit, from this end of the coil through the shorted MOSFET to the 12 volts. And what's on the 12 volts? Lots of capacitors to ground. So this end of the coil is connected via these capacitors to ground. And we know that to the SR meter, that is a very low resistance, almost a short, yeah? So from this end of the ESR meter, we have almost a short to ground, yeah? From this end, well, these capacitors were here all the time. But it didn't matter because this effectively was open circuit. Now it's not. So what do we see? Lots of capacitors to ground, which is almost a short to ground. So the equivalent of this circuit on the faulty phase is this. Yeah. Ground. Ground, yeah? And ground is connected together. Ground is ground, yeah? So when we put our ESR meter here and here, what do we see? Short, short, short. Yeah? That's why it's only read 0.002. Yeah? So the inductor is still reading 0.370 ohms, but we've got practically 0 ohms in parallel with it. Yeah? So let's have a chat about these things now. So this is an alleged ESR meter amongst other things. Yeah, it's a little component analyzer. And if we take a capacitor and we put the capacitor on it, then we switch it on. It reads the capacitance, it gives us an ESR. Okay, let's connect our oscilloscope probe to it. Well, it makes a very messy sort of like, yeah. I'm not sure what the frequency it is. It's kind of like the 100 kilohertz, but what a mess, yeah? What a mess that comes out of it. So, you can't use this in the same way I was using it to measure inductors. You can't use it to find short circuit high side MOSFETs and VRMs, because unless you have a capacitor in it, it won't give you the ESR. It doesn't tell you what the ESR is, yeah? It only does as a byproduct of measuring a capacitor. But as I've just proven, an ESR meter has far more uses than just testing capacitors, if it's a real ESR meter. But you can't call that an ESR meter, yeah? What's that you've got there? It's my ESR meter. It's not. That is not an ESR meter. That is an ESR meter. Yeah, that is an ESR meter. Said Crocodile Dundee or something like that. Yeah. So you'll not use this thing to measure ESR. Yeah, the nice little component analyzers, but it ain't an ESR meter. Buy yourself a proper one. Yeah. So there you go, guys. The humble ESR meter is not so humble. Yeah, this is one of the most useful things you can buy. It's one of the most powerful tools in your toolbox. Buy one of these and it will save you so much time and money and effort in repairs. It will pay for itself over and over again. I can guarantee you'll never regret buying one. I've had this one for 8 years. It's still going strong now. There are a number of brands available. Have a look around. These will not do the job. Simple as that. This will do the job. I can recommend this one because it's the one I have. It's the one I've used, and you've probably seen me use a lot on repair videos. So I have to recommend this. I know what it can do, and I've shown what it can do. This is not a sponsored video. I bought this myself many years ago, long before this channel existed. But I just wanted to show you what you were missing. If you've not got one, now you know what you're missing. Yeah, once you've bought one, you're going to say, thanks, Rich. Yeah, I'm sure. Okay, guys, hope you enjoyed that one, and I'll see you all soon on another Electronics Repair video. Ciao for now, guys.